is my pleasure today to introduce Christoff Tempesta, our speaker, who's a fourth-year PhD student in the Department of Materials Science and Engineering, as well as the Program for Polymers and Soft Matter at MIT. Ty received his bachelor's in science in materials science and engineering from the University of Florida in 2017. Despite still being a graduate student, Ty has authored 8 publications as well as a patent. He's received many awards, including the NSF Graduate Research Fellowship, the Lemelson Best Award, and the Martin Society Fellowship for Sustainability. Today, Ty will be talking about his graduate research in the Ortoni Group in the area of small molecule nanostructure design and applications to water purification. Really quickly, before Ty gets started, I'd just like to remind everyone that the talk is being recorded. We'd like to encourage you to stay muted for the entirety of the talk, as well as to turn your videos off to preserve bandwidth. If you'll please hold questions to the Q&A session at the end of the talk. You can ask questions at the end of the talk either through the chat, by raising your hand, or just by unmuting yourself and starting a discussion. So with that, I will turn it over to Ty, and I'm very excited to hear about your work.
Great, thanks so much for the introduction. Before I dive into the work itself, I just wanted to spend a moment to discuss the motivation behind designing these materials, and specifically the application which I work on, which is designing materials for water treatment. Prior to about 50 years ago, people who lived in Bangladesh primarily got their drinking water from surface water, whether that was collected rainwater, water from small lagoons, perhaps water that collected in puddles. But what arose was an epidemic of waterborne illnesses as these water supplies were contaminated with microbes. So in the 1970s, UNICEF and a group of global aid agencies went into Bangladesh and installed a vast network of tube wells to bring water from well below the surface to the surface for people to drink. But what they didn't know then, and what went unrecognized for nearly 2 decades, so until the 1990s, was that the water that they were bringing to the surface for people to drink was actually laced with dangerous levels of arsenic. And this is a problem that continues to persist today, nearly 3 decades later. There's around 20 million people in Bangladesh alone, of 140 million people worldwide, who continue to drink water laced with dangerous levels of arsenic. One of the most commonly deployed treatment strategies for water that's contaminated with heavy metals in places without centralized water treatment infrastructure is a bucket-based system like the one shown here. So if you look at the schematic on the left, essentially what you do is you pour contaminated water into the top of a bucket. It trickles through a variety of materials like sand, iron, bricks, and charcoal, and then clean water eventually comes out the bottom. Now, this type of system is effective at removing heavy metals, but as you can imagine, it has some pretty significant drawbacks. For one, these materials non-selectively absorb heavy metals like arsenic out of water. So in addition to removing heavy metals, it also removes other things from water that perhaps we care less about. And that ultimately limits the effectiveness and the lifetime of these systems for remediating heavy metals. Additionally, as you might imagine, these buckets are quite heavy, right? They're filled with sand, they're filled with bricks. And so getting these out to people is logistically challenging, and particularly getting them out to remote regions is especially challenging. And then at the end of their lifetime, you're left over with this physically large toxic waste stream. You have literally buckets that are enriched in arsenic. And so there exists this need to develop really effective water treatment technologies that are miniaturized for deployment in these types of situations. And so when we set out to work on developing materials, this was really my particular main focus. But over the last couple of years, there's been an increasing awareness of domestic water quality issues as well. In particular, there's been an increasing body of scholarly research that's looked at the intersection between where drinking water violations are located in the United States and where populations of color are living. And as you're probably unsurprised to find out, there's a pretty strong correlation between those two factors. The United States itself is no stranger to having heavy metals in its water supply. There continues to be a persistent crisis in Flint, Michigan, for example, where there's lead that's leached into drinking water. So as you can imagine, there's quite a few different solutions that are needed to solve these problems, but developing new materials that are highly effective at remediating specific heavy metals from water is a part of those goals. When our group thinks about designing new materials, we're inspired by small molecule self-assemblies in nature, like the cell membrane, which is shown here. As you may know, the cell membrane consists of small molecules called phospholipids that have two parts. One part of these molecules is a hydrophilic head group, which is shown in red on the schematic, and the other part is a hydrophobic tail group, which is shown in gray. When you put these small molecules in water, they spontaneously form a nanostructure like the one shown here, so that the hydrophilic head groups form the outside of the nanostructure to very favorably interact with water in its environment, whereas the hydrophobic tail groups aggregate into the center of the nanostructure so that they don't have to interact with water. And these types of self-assembled systems have a variety of benefits that would be really interesting for engineering new materials. For one, we can really easily modify the surfaces of these materials by designing the hydrophilic head group for a specific application. And so that can be really impactful in designing new materials, for example, for water treatment. Additionally, small molecule self-assemblies have very high surface areas, and this is a result of moving towards nanomaterials. The dimensions of these materials are actually determined by the dimensions of the molecules themselves. So in many cases, you can produce nanostructures with, for example, thicknesses or diameters that are less than 10 nanometers. And moving towards really high surface area to volume ratios is critical if we want to develop miniaturized treatments for something like water treatment. Small molecule self-assemblies also have a propensity for self-healing. Because these materials are held together exclusively through non-covalent interactions, if you disrupt a cell membrane or disrupt a small molecule self-assembly, it has the capacity to repair itself because it doesn't want hydrophobic parts of molecules exposed to the solvent environment. However, small molecule assemblies typically, conventionally, have limited internal cohesion. In other words, the molecules which make up these assemblies are very dynamic. So for example, a phospholipid can move around really easily within the bilayer. It can flip from one side of the bilayer to the other, or it can actually exit the bilayer altogether and enter into another one. These types of dynamics are really important in biological systems, but we believe they've hindered the ability of small molecule assemblies to be used in more demanding environments. And so we believe that if we would be able to suppress this type of dynamic motion, we would be able to use small molecule assemblies in more demanding contexts. And so today I'll be sharing our work to that end, and it's really split into two major parts. The first is designing robust small molecule assemblies by incorporating strong intermolecular interactions between molecules. And I'll also touch on our work in incorporating responsiveness into this molecular design. And then the second part will be applying these materials to the remediation of heavy metals from contaminated water. And so with that, I'll go ahead and dive right into the first part, which is designing this robust self-assembly platform itself. When we thought about designing new amphiphiles, we had this sort of overall design principle, which is shown on the left, where like any other amphiphile, we keep a hydrophilic head group and a hydrophobic tail group. But what we add is a new domain called a structural domain into the molecular structure. And our idea behind this domain was that once these molecules had assembled, it would provide strong, dense intermolecular interactions to really slow down the dynamic nature of small molecule assemblies. We screened and synthesized, let me assure you, dozens of different molecules to find the right parameters to allow self-assembly to occur. And we ultimately ended up with these three amphiphiles, which are shown on the right. From bottom to top, these amphiphiles all have a short branched aliphatic tail group. They have 3 aramid repeat units, or aromatic amide repeat units, that are inspired by the structure of Kevlar, hence the name of the talk. And then they have a hydrophilic head group. From left to right, we have an anionic head group, a zwitterionic head group, and a cationic head group. And we made these 3 amphiphiles to see if changing the surface charge would have any effect on the assembly properties. So when we put any one of these molecules into water, we observe that they spontaneously form nanoribbons, like the ones that are shown in the center of the screen on TEM and cryo-EM. These nanoribbons have dimensions on the orders of 4 nanometers tall, 5 to 6 nanometers wide, and up to 20 microns in length. So the cross-section of these materials is very small, and they're also very high aspect ratio materials. So the first question that we had once we got this far, once we created these self-assemblies, was, did including this structural domain actually slow down the dynamics of our nanostructures? So we designed an experiment that's shown here on the left, where we created 2 separate populations of nanofibers. One of these populations is labeled with fluorescent donors, which are shown in that bright green, and the other is labeled with quenchers. If a fluorescent donor comes into contact with a quencher, as the name implies, the fluorescence is quenched. And so that's what's shown sort of on the bottom of this slide. In conventional sort of prototypical small molecule assemblies, if you perform an experiment like this, as I mentioned, the molecules are able to leave one assembly and exit and enter into another one. And this type of dynamic motion can happen on the order of a couple of hours to produce totally homogeneous assemblies like would be on the bottom. So we performed this experiment on our own materials. And what we observed was not only was this not happening over a few hours, it wasn't happening over the timescale of months. So we had totally suppressed the ability of molecules to migrate between different assemblies. Then we really tried to make this type of dynamic motion favorable. We turned the temperature up to 80 degrees C. We turned the concentration up to try to promote crowding between different nanofibers. And even in that case, we didn't observe that molecules were moving between different assemblies. So by including this structural domain, we had totally hindered the ability of molecules to move between assemblies. That led us to start wondering, what did incorporating the structural domain do to other properties of these small molecule assemblies? And so we next turned our eyes to looking at the mechanical properties of the individual nanoribbons. We performed a range of indirect mechanical testing experiments, and the results of those are shown on this slide. Specifically, we looked at the strength and the Young's modulus, or the stiffness of our nanoribbons. And in both cases, we extracted that the strength and the stiffness are on the order of 1 to 2 gigapascals, which places the individual nanoribbons roughly in the vicinity of silk. We were excited not only by the numerical value of these measurements, because that's honestly a really great place to be for applying assemblies to engineering applications, but also by the fact that we were able to measure these properties at all. In many cases, using the techniques that we employed, small molecule assemblies would simply fall apart under the testing conditions. And so really the capacity to test for these properties itself was very exciting to us. And then finally, we really wondered, how far can we push the envelope on these materials? If you take a conventional small molecule assembly, like the cell membrane, you put it outside of water and you let the water evaporate. In most cases, the assembly will fall apart because the driving force for it to take on a particular nanostructure is the presence of water, right? Is the hydrophobic domains trying to get away from water in its environment. We believed in our case, we might actually be able to retain the nanostructure outside of water because of how tightly those intermolecular interactions would be holding molecules together. So what we did is we applied some processing techniques to the nanoribbons. We heated them, and we gelled them, and then we drew them into a salt bath. And that's what's being shown on this slide here. So we're actually able to create a thread of these nanoribbons in water, and then pull the thread out of solution. And this was really, really exciting to us, because as best as we can tell, small molecule self-assembly or self-assembled materials have never been used previously in the solid state. We were then able to dry these threads and perform some testing on them. The first testing we performed was X-ray scattering experiments. And the outcomes of these experiments, as you can see on the profile on the left, was that there was organization maintained on multiple length scales. For one, the molecules themselves remained organized within the nanoribbon assemblies. And then one layer above that, the nanoribbons were remaining highly aligned with respect to each other. We then looked at the mechanical properties of these threads. On the left side is just what I think is a fun photograph of a 0.1 milligram 0.1 milligram thread holding a 20 milligram weight. But perhaps more scientifically on the right side, we showed that by modulating the counterion that we gel the nanoribbons with, we're actually able to change the mechanical properties of the threads themselves. And so with that, we had created this underlying platform for robust molecular assemblies. And we switched gears a little bit to wonder, could we actually now think about how we could break apart these assemblies? For example, thinking about how we might be able to recycle them. So we came up with this additional design principle shown here on the slide. So on the top is a conventional Aramid Amphiphile assembly. As I mentioned before, it has a hydrophilic head group, a structural domain, and a hydrophobic tail group. And we thought if we incorporated a photoswitchable group into the middle of this structure, which under UV irradiation changes the nature of the molecule quite significantly, or the geometry of the molecule, then it might actually be able to break apart these assemblies. So we synthesize this molecule shown all the way on the left, where from bottom to top, we keep a short branched aliphatic tail. We have these Aramid repeat units to provide that structural stability in blue. We have a cationic head group in purple. And what we've added in the middle of this structure is a pink photoswitchable vinyl nitrile group. Under UV irradiation, this molecule goes from its trans to cis isomer. And if you heat this molecule, or if you heat a vinyl nitrile group, it reverts from its cis back to its trans isomer on the left. When we synthesize these molecules on the left, the trans isomer, as before, they spontaneously form these nanoribbons in water with very similar dimensions as to what we observed before. And when we irradiate these molecules, over the course of 1 hour, we see that an isomerization process happens. So this is just simply a UV vis absorbance profile. It starts at the green line, over 1 hour, it goes down to the blue line, and then there's no changes observed from there on. So we're able to see that we can induce this photoisomerization event. And the question we had was, did that in fact break apart the nanostructure? The answer to that question was a resounding no. Instead of breaking apart the nanostructure, we ended up with a totally different nanostructure, which is these nanotubes that are shown on the left. They're about 25 nanometers in diameter, and the wall thickness of them is approximately 5 to 6 nanometers. In the middle, we see the transition state from the nanofibers to the nanotubes. What we can see, and when we capture this intermediate state, is that the nanofibers are coiling into themselves, and eventually they fuse together at their edges to form the nanotubes that you see on the left side. Interestingly, we tracked the UV vis profile of this nanotube solution over the course of 6 months. And as you can see, there's no change in the profile over that time period. What that means is that the nanotube morphology is maintaining its state over 6 months. And this was a really exciting result for us. If you take a conventional photoswitchable group, like an azobenzene or the vinyl nitrile group, and you incorporate it into a molecular structure, in most cases, under thermal energy, it will over time revert back to its initial trans state. This can happen on the order of below the second time scale to, on the long end, usually on the order of days. But for these structures to maintain this type of metastable state over 6 months is really quite unusual. At this point, we wondered, have we effectively locked it into the state, or can we actually go back to our original nanofiber morphology? What we observed is that if we heat these nanoribbons up to 80 degrees Celsius for 1 hour, we are actually able to return to the initial nanofiber morphology, which is shown in that TEM in the middle. On the graph on the left side, what we're doing is simply observing the UV vis profile over the course of 5 cycles where we irradiate and then heat and go back and forth. And as you can see, we can switch between the morphologies at least 5 times without loss. And then finally, we tried to capture the intermediate state of this transition, which is shown on the right. What we observe is that as we heat these nanotubes, the nanofibers are released at the interfaces on the edge of the nanotubes. And so with that, I'll pivot to our last piece of work, which is applying these Aramid Amphiphile assemblies to water remediation, to remove heavy metals from water. And the design principle behind that is shown here. Specifically, what we'd like to do is select hydrophilic head groups, which are shown as these dark blue circles that have two purposes. One is to be sufficiently hydrophilic to induce self-assembly. And the second is to have an additional ability to remediate heavy metals like lead from water. For these experiments, we've produced two different amphiphiles. And for the sake of clarity, we'll just track one of them for the next few slides. But pretty much in all cases, they had very similar patterns. So one of the molecules we created is shown here on the left, where from bottom to top, we have this short branched aliphatic tail group as before. We have 3 aramid repeat units as before. And then on top, we have a chelating molecule. This molecule is called tetraxidin. It's a pharmaceutical compound you might get if you went to the hospital for heavy metal poisoning. It's also used to complex to MRI agents. It's also used, I guess, to complex to heavy metals for MRI imaging because of its strong propensity to couple with heavy metal ions. So we synthesize this molecule, and as before, as you can see, it forms nanoribbons with very similar dimensions, 4 nanometers tall, in this case up to 9 nanometers wide, and tens of microns in length. So the first question we had, of course, was, now that we've created these nanostructures, do they actually remediate lead from water? The easiest way to look at this is through UV vis spectroscopy, where there's an emergence of a peak at around 265 nanometers, resulting from a complex between the tetraxidin head group and lead ions in solution. As you can see, this peak grows and grows as we titrate more and more lead into solution, and ultimately plateaus at around 50 mol% lead, indicating a 2-to-1 stoichiometry of binding between the amphiphiles and lead that's present in solution. From there, we sort of do our homework to learn more about this binding process through 2 other types of experiments. In the middle, we perform isothermal titration calorimetry. This is a calorimetric experiment that tracks the amount of heat that's released as we inject a concentrated lead solution into a solution of nanoribbons. And the heat is released as a result of the binding between those 2 species. What we extract from this is an equilibrium binding constant, which is shown on the bottom. And as you can see, it's on the order of 10 to the 5th, which indicates a very strong binding event between the nanoribbons and lead that's present in solution. And then finally, we perform a range of lead adsorption isotherms, which are shown on the right. The information that we extract from these absorption isotherms is the saturation capacity of the nanoribbons. In other words, per gram of nanoribbon, how many milligrams of lead can they soak up from contaminated water? And in this case, for this particular for this particular instance that's shown, a gram of nanoribbons could remediate 72 milligrams of lead from solution. So at this point, for the purposes of comparison, I'll bring back the 2 molecules that we've worked on. So the top is the tetraxidin head group molecule that I was just talking about. On the bottom is a pentetic acid head group molecule, which is an analog of EDTA. And first, we looked at these adsorption isotherms over a range of pH values. So first, if we just look at pH 7, you can see the pentetic acid head group molecule absorbs more lead from solution than the tetraxidin head group molecule. On the order of essentially 1/10 of its weight, it can absorb lead. The next trend that we observe is that as the pH decreases, the amount of lead that's absorbed also decreases. And this makes sense because as these head groups become protonated, the ionic interactions between the head groups and lead that's present in solution decreases. And then finally, we wanted to look at what effect would competing counterions in solution have on the remediation capacity of these nanoribbons for lead. So we added equimolar amounts of lead and some other species like calcium, nickel, or copper into the solution and tracked how much lead was absorbed in those cases. For both molecules, as you can see, adding calcium or magnesium has a very minimal effect on the amount of lead that's absorbed, whereas copper and nickel compete more strongly for that complexation spot, and the amount of lead that's absorbed is less. So sort of the outcome from these experiments was that by selecting the head group you can not only affect how effective the nanoribbons are at remediating lead, you can also affect their sensitivity to pH, and you can affect their selectivity for particular ions. You'll notice, for example, the pentetic acid head group amphiphile is less affected by calcium and magnesium than the tetraxidin head group molecule. And so with that, I'd just like to quickly summarize what we talked about. So first, I shared our work developing a robust self-assembly platform. By incorporating a structural domain into the amphiphile design, we were able to suppress exchange dynamics between nanoribbons. We saw that incorporating the structural domain also produced nanoribbons with silk-like mechanical properties and enabled the translation of these nanoribbons to solid-state macroscopic materials. We then looked at incorporating photoswitchability into the molecular design and saw that through that, we produced nanotubes, which were able to maintain the metastable isomer state of the molecules for over 6 months, or for at least 6 months. And then we looked at applying the Aramid amphiphile platform to remediating contaminated water by designing the head groups of the molecules to pull lead ions out of solution. And so with that, I'd just like to take a moment to thank everyone who's helped work on these projects. I'm in Professor Julia Ortoni's group in Material Science and Engineering, and virtually anyone who's worked in our lab has contributed to these projects. I'd also like to give a special shout out to the folks at the MIT cryo-EM facilities, the MIT.nano cryo-EM facilities for helping produce many of the cryo-EM images shown in this presentation. And of course, I'd like to thank all of our funding agencies who have made this work possible. And with that, I'm more than happy to answer any questions that are out there. Thanks so much.
Excellent presentation, Ty. We can take questions now, and I guess while everyone is thinking of questions, I can get started with one. So the heavy metal work you showed was really cool. How adaptable or modular do you think your system will be to other contaminants in water?
Yeah, that's a great question. And I think that's really one of the benefits of using a self-assembled system is the capacity to change the head group to look at addressing other contaminants. And so that's actually something that we're looking at. It's one of my main thrusts. So the answer is hopefully easily.
And kind of a follow-on to that, how hard do you think it would be, or do you think it would be possible to actually get self-assembly or maintain self-assembly with mixed head groups?
Yeah, that's a great question. Certainly one of the advantages of self-assembly is that you can incorporate multiple amphiphiles with different functionalities into the same structure. And so there's a few things we're looking at in that area. Some things we've already done have been co-assembling, for example, the heavy metal remediating groups with other charged head groups to see if that would have any impact on the remediation capacity. And we observed in that case, there was actually pretty much no effect. Something that's, I think, interesting about our amphiphile design is that unless you sort of hit the design parameters right, the Aramid amphiphiles like to exclude differently looking amphiphiles from within them. And that may in some cases extend to the head group as well. And so we're kind of looking into that to see what the capacity is for co-assembly.
That sounds really exciting. Does anybody else have questions?
Yeah, I have a question about the disposal process. Once the nanoribbons absorb the lead and so forth, what is the process to get rid of the lead in the field? You mentioned that in Pakistan and Bangladesh, for example, that there's all this contaminant that is difficult to dispose of. What's the process for getting rid of the lead? Is it possible to use some chemical reaction to take it out of the nanoribbons and put it in some safe place, or how does that work?
Yeah, that's a really interesting question, and also an area of research for us. I had sort of previously hypothesized that simply by changing the pH, we might be able to disrupt the interactions between these chelating head groups and the lead to sort of effectively recharge the nanofibers. But as you saw, even in the cases where the head groups are mostly or fully protonated, they still have the capacity to remediate lead from water. And so in that case, it doesn't seem like we can fully recharge the head groups and use them again. It is relatively simple from a high level to just remove the nanofibers from water. They can be centrifuged down because their density is higher than that of water. So you can just kind of take the clean water out from that. But it's a great question, and it's an ongoing area of research for us.
David, you can go ahead again. Feel free to.
Thank you. I don't want to monopolize the conversation, but is it possible that you have a slide that shows the way that lead is absorbed or chelated in the nanoribbon and so forth? Is there some sort of attachment chemically, or is it physically bound, or what is the process for effectively isolating the lead in the water solution?
Yeah, that's a great question. I unfortunately don't have a specific slide for that, but if I can go back to the molecular structure, essentially what happens is, maybe I'll even put some annotation to work here. So the lead ion will go into this spot where the star just showed up in the center of these molecules. And what happens is each of those 4 nitrogens and the 3 carboxylic acids sort of wrap themselves around the lead ion. So it's not any sort of covalent interaction, but it is multiple very strong ionic interactions that result in the lead ion being bound effectively to that spot. And that's what makes it difficult to remove afterwards. So yeah, perhaps another answer to your question is we could also look at more transient type of interactions that would more weakly complex with heavy metal ions to remediate the lead as well, and then recharge the nanoribbons.
Thank you for your response. That was a fantastic presentation.
Thanks so much.
It doesn't look like there are any other questions, so I'll ask another follow-on to this. When you think about water remediation and potentially kind of recyclable or reusable materials, how do you think about balancing the strength of the interaction with what you're trying to capture with being able to release it later on? So I know there are other chelating agents. What have you tried? What have you thought about for that?
Yeah, I think our first pass at this problem was really just sort of capture and remove. And that is, I think, probably the status quo for a lot of water treatment technologies today, right? Is you basically, even with these bucket systems, right? You capture it, you saturate them, and then you swap it out for something else, which perhaps in the long term of a material's lifetime is not the most sustainable option. Most of our work in this area has been looking at removal of arsenic. And that's been a particularly challenging problem because the chelators, which have high affinities for binding to arsenic, are not very hydrophilic. So they're not sufficient enough to induce self-assembly. But the mechanism for binding arsenic is different than ionic interactions. In that case, it's often a sulfhydryl arsenic binding event. And you can, in theory, undo those types of chelation events with like redox type reactions. And so that using a totally different mechanism would be a way to recharge the nanoribbons. The key there being able to actually make those nanoribbons.
That's fair. That's really interesting. Any other questions? I feel like I'm dominating the Q&A.
I don't want to monopolize the conversation either, but I had a question about the expense and the weight of the material with respect to getting it into the field, for example, in Bangladesh to actually use. You mentioned that the sand and the brick mixtures and so forth are very heavy. I was wondering what the corresponding situation is with these nanoribbons. Are they assembled in the field, or are they brought in mass, or how does that work?
Yeah, that's a really interesting question. I think one of the coolest factors of the materials that we've made is that they can actually be scaled somewhat easily. We use primarily well-established coupling reactions. These are sort of established peptide reactions. And so the chemistries behind creating these are not too complex. And the processes to make them are already industrially existing, let's say. That being said, it's of course always hard to estimate the real world cost of a material when you pay lab scale prices for these molecules. The platform itself, I would argue, is a relatively inexpensive material. And where we run into most of the costs in designing these materials is specifically in the head groups to follow the types of chemistries that we do. So I think there's certainly more work to be done in creating cheaper analogs of these materials that could be used. I don't know if that's necessarily the focus of our lab, is working to drive down those costs. As to where they would be created, I think an active area of research for us, as I mentioned, was looking at translating these materials to macroscopic materials. And so I think ideally we would not necessarily be using like nanoribbons that you would centrifuge down, but rather could you make sort of these threads into something that's usable for people to use. And then you could perhaps dip a fabric of these nanoribbons in water and pull it back out or something like that. So ideally, I think it would be something simple and prefabricated that could be deployed for remediating these heavy metals.
And could I just follow up for a second? Are there other uses of these very strong nanoribbons that you can imagine? I can think that these materials have extraordinary properties and so forth. I was wondering if you've given any thought to what they might be applied to, other than the the chelating environment.
Yeah, absolutely, and that's kind of the work of other people in my lab as well. Sort of the things that come to mind off the top of my head as sort of a function of having these really high surface areas and really stable materials, they're likely a good platform for catalysis applications. Certainly there's an extended network of pi stacking within these nanofibers, so that might be good for electronic type applications. And I think other cases of environmental remediation, particularly in the solid state, would be really interesting as well. We were able to show that in the dried threads, we maintain approximately 200 meters squared of surface area per gram, which is an enormous amount of surface area. And so thinking about how having all of that surface area accessible on a solid state material, as I mentioned, I'm really focused in the area of environmental remediations. I could think of, things that might be present in air that we'd want to remediate as well, that would take advantage of that. I think there's one in the chat, Ariel.
Oh, thank you. Vladimir would like to know, would these materials be good as moisture barriers?
As moisture barriers? That's an interesting question. That is a very interesting question. Certainly the head groups are quite hydrophilic. So I would imagine if you made a solid state material, they would be very hygroscopic, whichever the word is. So yeah, I would think if we made some sort of solid mesh out of them, then they would be pretty successful at removing water from air. That's a really interesting idea. I think I'll have to bring that up and look into it more.
Indeed, there are many more questions to follow. I do want to thank Ty for opening up a great set of ideas to the rest of us. These are remarkable how flexible these materials are, and it's remarkable how well you can control them. Hence, I think we can keep on asking you next in the next opportunity that these might provide. But thank you so much for today.
Yeah, thank you.
Yeah, so let's all thank Ty one more time with either visual hand claps or the hand clap reaction. Great talk, Ty, and beautiful figures, by the way. And I just want to let everyone know that the next talk will be April 27th, 2021, and it will be by ENS Eric Einsa, PhD candidate in EECS and the MIT Lincoln Lab. And we are excited to hear about his work too. So thank you again, Ty, and I hope everyone has a great week.